Hello, and welcome back to the Aquifer. I'm Ted Bennett. In this segment, I'm excited to discuss a topic that's always been a bit of a puzzle for me. Every time I start thinking about pump horsepower and motor sizing and motor and pump efficiency, I find myself pulling out my Cameron Hydraulics book and the equations about pump and motor and system efficiency. I always felt like I was starting from scratch. I felt like I had to learn it all again, every single time. Have you ever had a pump supplier tell you that a pump is power limited? That was always a puzzle for me. I decided that I was going to put all this down in one spot so that I could once and for all have everything related to pump, power, and efficiency captured all in one place. In this segment, I will show you how VFD, motor, and pump efficiency impact the power needed for the system, and I will show you the basics of motor selection. Once the motor selection is made, I'll show you what it means if a pump is power limited. I'll also help you to check your system's performance to see if power limiting is really a concern or not. It actually depends upon your system, really. So yeah, this one's a bit selfish for me, but I think you'll enjoy it too. Okay, so here's what we're talking about. Here's a diagram of how power flows through the system, from the utility on the left side all the way through to the water on the right side. You have the power coming in to the system from the left side here, and the power passes through the VFD, if you have one, then through the motor, and from the motor, the power then passes to the pump, and the pump delivers the energy to the water to begin moving it. As you may recall from previous videos, pumps basically add energies to a hydraulic system to lift water from one location to another location. This is how energy is routed into the pump. So what is efficiency? Basically, it's the ratio between the power and energy input and the output power and energy. It's like a batting average. It's a measure of how much energy is lost to friction or wear in the object. Here we're showing you the motor. So each component of the system has some efficiency associated with it, and energy is lost through each device. At the end of the computation, you'll of course find that you need to apply more energy to the system on the front end to get the proper amount of energy out of the pump and into the water. And here's an example of a pump system. In this case, the VFD is rated at 95% efficiency and the motor 93% efficiency, while the pump is rated at 75% efficiency. We could say that the entire system is rated at 66% by multiplying all these together. Now, I often see the pump and motor combined, like in a submersible pump application, and here we would say that 93% times 75% is going to yield something like 69.8%. So we've got the efficiency down. So here's an example of how horsepower is calculated. All this is headed towards picking out a motor for the pump. And to do that, we need to figure out how much horsepower is needed to be supplied to the pump. And here's the general equation for horsepower based upon flow in gallons per minute, head in feet, specific gravity of the fluid, which for my work is generally 1 because I usually work with water, and the 3960 is the conversion factor so that we can get all this into horsepower, and E is the efficiency. Okay, I know, the electrical engineers are going to start posting negative comments, so I'll say right now that yes, we should be using kilowatts as input power. I know, but bear with me. For the sake of this presentation, I'm going to stick with horsepower. If you want to do the conversion, here it is. Get nuts. All right, back to the presentation. Here are the horsepower terms that I'll be using. I will be calling input power the power to the supply side of the motor. Then I'll call shaft power the power supplied by the motor to the pump. You could also call shaft power the brake horsepower in a situation where we have a direct drive pump, such as a submersible pump, which is, I think, the case that we're going to do here. Okay, here's an example of how the horsepower supplied to the pump, or the shaft horsepower, will be calculated. We know that we have a flow needed of 3,500 gallons per minute at 150 feet of head. And using a 75% efficient pump, we can determine that we need to have 177 horsepower supplied to the pump, the shaft horsepower. All right, now we'll show you the rest of the system related to this 177 horsepower. Realistically, the 177 horsepower delivered to the pump from the motor in the previous slide actually becomes 133 horsepower delivered to the water by the pump, because if you remember, the pump is only 75% efficient. Now, working the other way, in order for the motor to deliver a 177 horsepower shaft or brake horsepower, it must be supplied with 190 horsepower. Yes, electrical engineers, you can convert this to kilowatts and do your math. But all this demonstrates the effect that efficiency has upon the power needed in both directions from the pump. Energy and power is dissipated by each component in the system. All right, finally, we're at the key discussion point. We're going to select a motor. And we're working with a European pump supplier here, so we've got some unusual horsepowers available, but bear with me. Let's assume that we've picked a 185 horsepower motor, since that will exceed the needed 177 horsepower for our particular duty point of 3,500 gallons per minute at 150 feet of head. Remember, motors are guaranteed to supply the nameplate horsepower, which in this case would be 185 horsepower. Now here's a couple of plots of some curves. This is what you're going to get from a pump supplier. The pump performance curve is shown here in red. This is a normal head versus flow situation. There's nothing new here. Then we're plotting the shaft or brake horsepower here in the blue line. And it's actually plotted on the right side secondary axis. And this shows the horsepower we need at each flow and head point. And now remember, we picked a 185 horsepower motor. And as you can see, our horsepower curve actually exceeds 185 horsepower here on the right side in the orange area. This is what it means when our pump is horsepower limited. This basically means that the 185 horsepower motor is not large enough to deliver the needed horsepower if our flow exceeds 4,000 gallons per minute. The selected 185 horsepower motor is not large enough. And the question is, can this situation ever happen in your system? And the way that I would analyze this would be to look at your system curve and see how likely a flow of 4,000 gallons per minute and the corresponding head of like 120 feet of head would be. I'd suggest that you look at the length, diameter, and fittings losses, and possibly the pipe roughness assumptions that you made to develop your system curve. Then compare that with the flow in head beyond this overload point. In most of the cases that I look at, the overloading issue is not significant, but it can be, and it's something to be aware of. All right, let's assume that you needed to avoid the power limit. Basically, this is pretty easy. All you would need to do is choose a larger motor, which in this case, the next largest motor size is 215 horsepower. Yes, again, European horsepower options. And now, one thing of caution, I've seen a lot of standard specs that come from engineers that require that the motor is non-overloading in the entire performance curve. But I think these engineers should be careful in weighing this statement, because this requirement could be adding cost for a larger motor than is feasibly required. Because if your system is not likely to get beyond the overload point, maybe like in our example, you could get by with 185 horsepower motor. So choose wisely and be careful. I hope this information was helpful to you. I know that putting this together was very, very helpful for me. Hey, like always, thanks for watching the Aquifer. And if you like this video, please share it and give me some feedback. And like always, have a great day.